Welcome to Chapter 2, Types, Operators, and Expressions. So again, I'm not going to tell you everything. I want you to read the book. The book does a great job. I'm just going to call your attention to some things that might seem a little bit weird if you're coming from a language like Python or JavaScript or even PHP, where things are objects and you don't even notice it. You've been using objects your whole career and you didn't even realize it. So we're going to talk about data types and storage allocation. One of the things that you just gotta, part of what I love about teaching this historical view on C is that we have to talk about storage allocation. Float and double worked out pretty well, partly because in the early days of C they did them all in software, so they just made them easy and they made them work well. They weren't expected to be fast. The things that they wanted to be super fast were like the integer and byte data, character data. Type conversion. And then there's a story that connects integer division in Python 2 and all that pain of Python 3 and how division changed and why it was the way it was and how that worked. And again, it has to do with performance and simple decisions that got made, sadly. Bitwise logical operations, we'll talk about them. You're probably not going to use them, but it's really important in a historical context to understand why they were so thorough. And it really had to do with the fact that because of word-oriented computers switching to character-oriented computers, all of us programmers were thinking in words, and if we didn't see shifting and masking and bitwise stuff, we'd be like, I can't program in this thing, because a lot of our work in those word-oriented computers was masking and shifting. And so it's like we had to have it. We didn't use it as much as we could have thought. So let's start with division. In the good old days, we were not worried too much about doing division. And if you were doing division and you cared about the division, you were probably doing it in floating point because you were doing scientific computing and you did that on supercomputers. You didn't do that on general purpose computers. Unix was really designed for general purpose computers. And in general purpose computers, you sort of thought to yourself, why is division that important? And I'm sure they made some decision somewhere. I do not know why. It probably had to do with one of the computers they were working with had truncating division in hardware and non-truncating division in software. I don't know, or rounding division or whatever. A lot of those computers didn't even have fast floating point, so some of the computers they were working on did all the floating point in software. And maybe they even did integer division in software with loops and stuff. But we don't know. I don't exactly know, but they made this decision to do integer division truncating. And this was one of the biggest things of going from Python 2 to Python 3 that was the most painful. So Python 2 was like over 25 years old, and it wasn't that long after C that Python 2 was written. Python 2 was written in C. And Python 2 to Python 3 transition was a big deal. It took a long time. It took 12 years to get there. But Python 2 was like the greatest thing ever, except for a few things. Because Python 2 was so related to C, the strings in Python 2 natively were ASCII, not Unicode, which meant it couldn't even do like Spanish characters, let alone Asian characters. The print was part of the language, and the programmers got a lot of help. Like they got an automated code converter and syntax checkers, and they did all kinds of things where they would take certain libraries like the print function, and they would put it in Python 3, and then we backport it to Python 2, so you could like switch from using the print statement to the print function. And there were lots of things that made this transition as easy as possible. The one thing that they really never could crack, and we just had to bite the bullet and get used to it, was Python 2 returns integer, and the division is truncated. So if you do 3 divided by 4 is 0 in Python 2. And in Python 3, it's integer 3 divided by integer 4 becomes floating point 0.75 because that's what calculators do. And the Python 2 division truncated because it didn't seem like it mattered much back in the 80s, and C integer division truncated. So 3/4 in C was 0, and 3/4 integer 3/4 was 0 in C, and so it was in Python. And 20 plus years later, that was the one thing we couldn't auto-convert, and Python 3 does it the way Python does. So It's less of a problem in C because C is actually a strongly typed language, which means if I wanted to say 3 over 4, I knew whether it was integers or floats, and I could force that. But in Python, you just, what's the variable? And so it imputes the variable type from the result of that expression. Whereas C has got to declare X as a float or a double or an int. So when a C programmer writes a division, they know already that they have to cast the values or use float constants to trigger type conversion in expressions. So as you're looking through the chapters, seeing these type conversions and casting, that's the kind of problem that was solved. But then Python simplified it and then made it really kind of yucky, and then they had to fix it. It's better in Python 3, and most of you have just learned Python 3, so consider yourselves lucky. So another thing they talk about a lot, and it has to do with as we start thinking about storage allocation on a bit-by-bit basis, we tend to need to know how to represent and print things out, not just in base 10. And it really has to do with the fact that base 8 and base 16 are better at printing out binary data, raw data. 10 is the number like where, how many pizzas do you want? I want 16 pizzas or 22 pizzas. It's our natural, the way we think, the way humans think. So to talk about bases, let's start by just reviewing what base 10 means. There is, the ones place and the tens place, and of course later there's hundreds and thousands, but the 4 in 42 represents 4 tens. So you can think of it as 4 times 10, which is 40. And then the ones place is 2 more. So 42 is 40 plus 2, which is kind of redundant. We do that instinctively. So now let's take a look at base 8. So 42 in base 10 is 52 in base 8. And what base 8 is really doing is it means that the digits in the two places mean something different. Meaning the 5 in 52 represents an 8. So there's 5 8s in this number that we're dealing with and 2 1s. And so 5 times 8 is 40 and 2 times 1 is 2. And so converting from 52 base 8 to 52 base 10, we get to 42. And we used base 8, and again, base 8 lines up perfectly with base 2 because 3 base 2 digits equals 1 base 8 digit. And I did a lot of base 8 in the early days, but base 16 is really the way we tend to do it now because it's a little more dense. The rightmost place is still the 1s, and the next place is the 16s. So the 2 in the 16s place represents 2 times 16, or 32. And then what's left over is 10, which we represent as A. And then 32 plus 10 is 42. Now the problem is we only have digits 0 through 9. So by convention, 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. F is all the ones. It's 4 ones. I know that. I just like 4 ones. So I can convert hex from hex to base 2 like very, very quickly. And if I need to look at a dump of some memory, I can dump it in hex, and then when I need to, I can convert it to base 2. So just converting back and forth between base 16 and base 2 is a bit of a trick. And I don't really care if you do much of this. You can grab this sample code and play with it. This is a conversion from base 10, a base number like 1, 2, 3, 4, to base 8 and then base 16. And the way this one does it is it converts the number in effect from the rightmost number up to the low digit up to the high digit. And so what you do is you use the modulo function. And so you take your number 1, 2, 3, 4 and you take it modulo 8, and what's left over as a remainder is 2. So that's the far right number in the new one. And then you chop it off with integer division. You chop that off and see what's left, and that's 154. And you're accumulating the 2 in the converted number. And then you take the modulo of 154, modulo 8, and you get 2. And then you chop off the next 8 with integer divide by 4, and you get 19. So now your bottom 2 digits are 2, 2. And then you do 19 modulo 8, and you get 3. And that next digit from the right is a 3. Then you divide by 8, integer divide by 8 to get what's left over. And that's below 8, and so that the fourth digit from the right is a 2. So 1, 2, 3, 4 in base 8 is 2, 3, 2, 2. And you can do the exact same thing. The difference is you got to look up the digits because the base 16 needs the A, B, C, D, E, F, and so I make a little string. Now, we're talking Python here. And so we do repeatedly modulo 16, integer divide by 16, modulo 16, integer divide by 16, modulo 16, integer divide by 16. And so we take 1, 2, 3, 4, and when we convert it to base 16, it kind of comes up from the bottom as 2D4, which we read 4D2. So that's just an algorithm that converts these. You tend to use this modulo, and that's how we can convert from one base to another. Now, it's not critical in this class. We're not going to spend a lot of time converting bases, but we just need to be aware that because there was so much awareness of how bits were stored, we tended to print a lot of stuff out in hexadecimal or in base 8, and so I just want you to know what those things are. So if you look, for example, at the ASCII chart that we've already seen, you see that it shows us that the letter A is 65, and in hex it's 41, and in octal it's 101, and in base 2, or binary, it's 1 and a bunch of zeros and a 1. And so this is just something that's making, and in the old days you had to be just much more aware of the real bits inside the computer, and hex and base 8, hex and octal, were better ways to sort of know what the bits were. So there you go. Now, another thing that C really was one of the early innovative language was byte addressable computers, right? And so we don't think much. Everything's a string, and we can look at the characters in the string. But in the old days, before C and the generation of computers that kind of triggered C, we didn't have characters. You couldn't, in the hardware, load a character. You could only load a word, and then you had to find the character within the word. And the language that really was the immediate precursor to C was the B language. And the difference is the B language was a really cool, low-level, word-oriented language, and then the C language came from B and became a byte-oriented language. And so C sort of said, we're going to do byte addressing. So if I take a look at the way I had to do character support in a CDC 6500, which is the computer I was using in 1975, 1976, it was a scientific computer. It barely cared about printing characters. It didn't even have lowercase. It had 60-bit words and packed 6-bit uppercase characters into those words. And it used a series of zeros to fill it up. And so if I put the word hello world into the CDC 6500, it took 2 words, and hello space WORL was packed into the first word, and D was in the second one, and then we did what was called zero filling. The rest of those characters were all zeros, the integer zeros, 0000000. And if I wanted to know what the 5th character of this 2-word string was, like the O, for example, you would create a mask. And in that mask, you would have zeros where you wanted to get rid of stuff and ones where you wanted to copy stuff. So you would take hello world and you'd run it through this mask with the bits in the right position, and then you would get the O and all zeros in the rest of the word, and then you would have to shift it half the way down because there were 10 characters, so you had to shift it 5 characters to the right, and then you would have the letter O in the bottom 6 bits of that word, and then I could write an if statement. That's how I would say if the 5th character is the letter O, I had to extract the 5th character by hand. So you can imagine how happy I was when I began to see programming languages that allowed me to use more of an array syntax and say string sub 5, or even in this case 0, 1, 2, 3, 4, string sub 4. But I could treat characters as an array. The notion of a character array for me in 1977 was, what? Why would you couldn't do that, right? And so we, a whole generation of programmers go through their entire career without having to do any masking and shifting. So this chapter is going to talk to you about it. And you might say, well, if C was so good at doing it for you, why did they show it? And that is that people like me would not have had respect for this language if it weren't for the fact that they had good masking and shifting, because we were doing that all the time in these word-oriented computers and word-oriented languages. And just as C and Unix were making the world safe for characters, then we had this other problem. And I'm only going to talk a little bit about this. Just don't worry about it. The concept of Endianness. So if you're loading words, do you load them with the least significant digits first or the most significant digits first? And most computers were big endian, and big endian to us software developers made the most sense because that's how we thought it would lay out. But it turns out that a few processors wanted to load, if they were going to do an add, they wanted to load the low end of the integer first so they could start the addition while they're bringing in the high end. And they could overlap the load and the add. And then Intel, which in those days wasn't all that popular, but they were so interested in the microprocessor performance that they became little endian so that their loading and addition were fast. And so we've been stuck with a lot of little endian microprocessors since then, and big endian and little endian. It's one of the harder things to solve, really. It really is. And so I'm going to show you some code. I really, all I want you to do is feel sorry for those of us who had to figure out little endian and big endian. And let me just give you an outline of what this code is doing. I'm not going to walk through it in detail. It just is kind of scary. So, and you're not even going to understand most of this code until chapter 5. It's just, let's just talk a little bit about the bits and how masking and shifting would have worked if we didn't have character arrays. So what I'm doing in this program is I'm creating a character array. The length of this character array is hello world plus 1 for the terminator, HELLO space WORLD. So 11 plus 1 should be 12 characters are allocated. And then what I'm doing in this next line that says int star SI is I'm actually saying I want to take this same storage and pretend it's an integer array. And so that's what that line is that it takes the address of the beginning of the first character and convert it from a pointer to a character, which is char s is a pointer to a character, and have it be a pointer to an integer. And again, I'm sort of like jumping ahead in chapter 5. So I'm not expecting to understand all this. I'm just making you aware of it. So in those first 2 lines, I've got a character array and an integer array. Okay? And this is a 32-bit integer, and so that means that the characters are stuck into 32-bit integers in a little endian way. And so if you look, that means that if you just look at memory from left to right, that the lowest of the first 4, which is 32 bits, the first character that comes out is the L, right? And you can see the little endian, which in your mind thinks it should be shifted, but that's because this is running on a little endian computer. And different computers will give you different results. And this is a little endian example. And so you can see with masking and shifting where I'm going to try to get the E out, which would normally be the second character, but it's kind of the second from the bottom of the first integer. And so what I do is I make a mask, and I'm going to print this out. I take FF, which is 8 bits of 1s, and then I shift it up 8 characters to the left, and you can see that in the printout. And then I mask out that character, which is the E, but then it's in the wrong position, and then I have to take that masked result and I have to shift it back down 8 so that it's in the bottom part. So now I can check to see what that letter is. This is how I would pull out the second character of a string so I could check to see if it's an E. Because I can't compare directly the second character of string, right? In Python, you're like, why are we doing this? And that's why you build a string class instead of use a character array for this. And I made it even worse by like starting with taking a character array and viewing it as an integer array and then playing with the integers. So, you don't have to understand this. just be thankful that you use Python. And if you don't use Python, you use C. And whether it's a big endian or a little endian machine, you can treat an array of characters as an array of characters, and you can get the third one or the fifth one with a square bracket notation. Okay? Storage allocation, storage allocation, storage allocation. So a summary of this lecture is we talked about number base conversion. We talked a little bit about division, why the Python 2 integer division happened. I don't really have a really good answer for that. Concept of integers and words and bytes and masking and shifting and characters, just because these topics are covered in this chapter and they will feel very foreign to you and unnatural. But just give them a shot, read through them, understand them, and they'll make sense later. Later we're going to learn about structures and pointers and addresses advancing and stuff like that. It'll all make a lot more sense coming up.